Fusion power, a proposed method of generating electricity through nuclear fusion reactions, involves the combination of two lighter atomic nuclei to produce a heavier nucleus, releasing energy in the process. Devices fashioned to harness this energy are called fusion reactors. The exploration of fusion reactors commenced in the 1940s, with only a handful achieving net power by 2025. To facilitate fusion reactions, a plasma state fuel and a controlled environment with specific temperature, pressure, and confinement time are required. The set of these parameters essential for a power-generating system is referred to as the Lawson criterion. In the cores of stars, the primary fuel is the lightest hydrogen isotope, protium, where gravity plays a role in enabling fusion energy production. Proposed fusion reactors would utilize deuterium and tritium, heavy hydrogen isotopes for DT fusion, the simplest to achieve as per the Lawson criterion, resulting in a helium nucleus and a high-energy neutron. Most designs strive to heat the fuel to approximately 100 million Kelvin. However, achieving the necessary combination of pressure and confinement time remains a significant challenge. Reactors must surpass break-even thresholds well beyond net plasma power and electricity generation for economic viability. Although fusion fuel is significantly more energy-dense than coal, the rareness of tritium on Earth, with a half-life of merely 12.3 years, poses a challenge. Consequently, in the operation of envisioned fusion reactors, lithium breeding blankets are exposed to neutron fluxes to produce tritium, completing the fuel cycle. Nuclear fusion offers several potential advantages over fission, including minimal high-level waste and enhanced safety measures. However, managing resulting neutron radiation that degrades the reaction chamber, particularly the first wall, presents a considerable challenge. Fusion research predominantly revolves around magnetic confinement, MCF, and inertial confinement, ICF methodologies. MCF systems, explored since the 1940s, concentrated initially on Z-pinch, stellarator, and magnetic mirror designs, with the tokamak emerging as the dominant MCF model post-verification of Soviet experiments in the late 1960s. ICF, evolving from the 1970s, focused on laser-driven fusion implosions. These designs are undergoing research on a large scale, notably through projects like the ITER tokamak in France and the National Ignition Facility, NIF laser in the United States. Researchers and private entities are also exploring alternative designs with potentially lower costs. Among these alternatives, interest is growing in magnetized target fusion and novel variations of the stellarator design. The terms fusion experiment and fusion device encompass a range of technologies utilized in the scientific exploration of plasma and technological progress. Not all of these technologies are capable of, or regularly employed for, generating thermonuclear reactions like fusion. The phrase fusion reactor is used interchangeably to describe these experiments or to refer to a theoretical power-generating version envisioned as the core of a commercial power plant, necessitating additional components such as a breeding blanket and heat engine. The Sun, akin to other stars, operates as a natural fusion reactor undergoing stellar nucleosynthesis that converts lighter elements into heavier ones while releasing energy. In the realm of nuclear fusion, fusion reactions take place when two or more atomic nuclei approach closely enough and remain in proximity for a sufficient duration that the nuclear force which draws them together surpasses the electrostatic force which pushes them apart, leading to the formation of heavier nuclei. For nuclei heavier than iron-56, the process is endothermic, necessitating an input of energy due to the significant repulsive force resulting from the multitude of protons in these nuclei. Conversely, for nuclei lighter than iron-56, the reaction is exothermic, yielding energy upon fusion. Hydrogen with its single proton requires the least amount of energy for fusion and produces the highest net energy output. The fusion reaction rate peaks at a specific temperature within the gamma window, with modern tokamaks achieving approximately 8 kPa 100 million Kelvin. At such extreme temperatures, the DT reaction becomes approximately 100 times more favorable than other reactions. The likelihood of a fusion reaction occurring is measured by its cross-section, denoted as S, which hinges on the relative velocity of the nuclei involved. Increased relative velocities generally enhance the probability of a fusion reaction, but excessively high energies can lead to a decline in this likelihood. In a plasma, the distribution of particle velocities can be represented by a Gaussian curve, or Maxwell-Boltzmann distribution, especially in a thermalized state. In such scenarios, using the average particle cross-section over the velocity distribution proves beneficial in determining the volumetric fusion rate. The Lawson criterion, formulated to evaluate the energy balance between energy generated in fusion reactions and losses to the environment, establishes the requirement for a system to produce more energy than it dissipates to generate usable energy. This criterion is contingent upon factors such as the efficiency of capturing fusion output, energy generated by fusion reactions, as well as conduction and radiation losses. Conduction, occurring when particles transfer kinetic energy upon impact with other substances, contributes to energy dissipation, with the rate influenced by temperature and density. Radiation, on the other hand, involves energy leaving the system as light and increases with temperature and ion mass. Fusion power systems must operate in a zone where the fusion rate exceeds losses. The triple product, delineated as the product of plasma density, temperature, and confinement time, plays a critical role in magnetic confinement systems, highlighting the necessity for generating adequate energy to offset losses. The achievement of fusion-relevant temperatures has been facilitated by various heating methods, with confinement time emerging as a primary challenge in modern fusion machines. Plasmas subject to strong magnetic fields encounter inherent instabilities, necessitating suppression techniques for prolonged operation duration. In contrast, inertial confinement systems enhance triple product values through higher density and brief confinement intervals. Energy capture strategies in fusion reactors encompass diverse methodologies, from utilizing neutron-capturing blankets to breeding fission fuel and harnessing charged particles in aneutronic fusion reactions for power extraction. Direct energy conversion techniques developed in the 1980s offer an efficient means to maintain voltage by utilizing fusion reaction products, demonstrating a notable energy capture efficiency of 48%. Plasma, an ionized gas capable of conducting electricity, is characterized in a bulk form by employing magnetohydrodynamics. This field of study combines the principles of the Navier-Stokes equations, which govern fluids, with Maxwell's equations, which dictate the behavior of magnetic and electric fields. Fusion, a process taking advantage of numerous plasma properties, includes the phenomenon of self-organizing plasma conducting electric and magnetic fields to contain itself effectively. Moreover, certain plasma types, like diamagnetic plasma, have the ability to create their internal magnetic fields, enabling them to repel external magnetic fields. In the realm of fusion approaches, various methods are categorized into color-coded families, such as the pinch family, mirror family, cusp systems, tokamaks and stellarators, plasma structures, inertial electrostatic confinement, inertial confinement fusion, and plasma jet magneto-inertial fusion. Magnetic confinement fusion, a prominent approach in fusion research, encompasses designs like the tokamak, spherical tokamak, and stellarator. The tokamak, epitomizing a well-established method, involves driving hot plasma in a toroidal shape with an internal current. On the other hand, the stellarator, conceived by Lyman Spitzer in the 1950s, emphasizes creating a twisted plasma path with external magnets, with examples like Wendelstein 7X, the world's largest stellarator. Moreover, within the realm of magnetic confinement, various configurations like magnetic mirrors, internal rings, bumpy torus, field reverse configuration, spheromac, and reversed field pinch present diverse ways to trap and stabilize plasma for fusion. Inertial confinement fusion, another significant avenue, revolves around techniques like indirect drive, direct drive, fast ignition, and magneto-inertial fusion. Additionally, inertial electrostatic confinement methodologies, including systems like the polywell, attempt to merge magnetic confinement with electrostatic fields to minimize conduction losses in fusion processes. Various modalities such as magnetized target fusion, muon-catalyzed fusion, and lattice confinement fusion showcase alternative paths towards achieving controlled nuclear fusion reactions. Lastly, the discussion extends to negative power methods like fusers and colliding beam fusion, highlighting diverse experimental approaches in the pursuit of sustainable fusion energy. Various approaches, equipment, and mechanisms are utilized across different projects to tackle fusion heating, measurement, and power generation. A deep reinforcement learning system was implemented to manage a tokamak-based reactor, controlling magnetic coils to govern plasma behavior more intricately than step-based systems. Collaboration between Google and California-based fusion company Tay Technologies in 2014 involved predicting plasma behavior at the Joint European Torus, JET. Additionally, DeepMind devised a control scheme for TCV. In the realm of fusion heating, methods like electrostatic heating, neutral beam injection, radio frequency heating, magnetic reconnection, and magnetic oscillations are employed to heat and contain plasma. Notably, neutral beam injection was crucial in achieving peak ion temperatures of 75 million K in the PLT, setting a world record surpassing the requirements for fusion. Another heating method is radio frequency heating, where plasma oscillates due to radio waves, akin to a microwave oven effect. Magnetic reconnection aids in quickly heating plasma when its properties change with density, enabling up to 45% of magnetic field energy to heat ions. Regarding measurement techniques, diagnostic tools for fusion reactors are extensive and diverse, encompassing flux loops, Langmuir probes, Thomson scattering, neutron detection, and X-ray detectors. These tools are crucial for analyzing plasma behavior, density, temperature, and neutron production essential for fusion reactions. Neutron blankets play a vital role in absorbing neutrons for heat generation, which can be extracted through various means like steam turbines or tritium production in breeder blankets. In the domain of power production, methods such as direct conversion and traveling wave tubes are explored to harness energy from fusion reactions efficiently. Direct conversion involves converting fusion product energy into directed motion, showcasing an experimental efficiency of 48%. Traveling wave tubes pass charged particles through a coil, generating electricity. The confinement of plasma is pivotal to maintain fusion conditions, involving equilibrium, stability, and conduction to sustain dense and hot plasma for fusion reactions. Magnetic confinement methods like magnetic mirrors and magnetic loops are crucial for confining plasma effectively, offering different advantages and disadvantages in diverse fusion reactor designs. Electrostatic confinement fusion devices like the fuser utilize electrostatic fields to confine and heat plasma for fusion reactions. Further advancements in fusion technology continue to explore innovative approaches to enhance fusion power generation. The heavier isotopes of hydrogen, deuterium, and tritium are the primary fuels considered for fusion power. Deuterium is abundantly available as semi-heavy water on Earth, while tritium, with a 12-year half-life, must be produced. Fusion reactor designs include a proposed lithium breeding blanket technology surrounding the reactor. Helium-3 is a more speculative fuel source that would need to be mined extraterrestrially or produced through other nuclear reactions. The protium-boron-11 reaction is highly theoretical but offers the advantage of minimizing neutron radiation. Tritium, a natural isotope of hydrogen, is challenging to find, store, produce, and is costly due to its short half-life. For the deuterium-tritium fuel cycle, tritium needs to be bred from lithium using specific reactions, where neutron multiplication materials like beryllium and lead play significant roles. The process involves reactions with 6Li and 7Li, with 6Li being exothermic and 7Li being endothermic, but not consuming the neutron, helping to keep neutron populations high. One of the drawbacks of DT fusion power is the significant neutron activation of reactor materials and the high percentage of energy carried off by neutrons. Neutron flux in a commercial DT fusion reactor is about 100 times that of fission power reactors, presenting challenges for material design and handling radioisotope tritium. In the case of deuterium fusion, fusing two deuterium nuclei results in reactions that produce tritium and helium-3. Removing tritium quickly while allowing helium-3 to react leads to a fuel cycle called tritium-suppressed fusion. This approach eliminates the need for materials resistant to fast neutrons in the fusion reactor. Deuterium-deuterium fusion, while not tritium-free, offers advantages such as independence from lithium resources and a softer neutron spectrum compared to deuterium-tritium fusion, where tritium breeding is necessary. Another fusion approach involves combining helium-3 and deuterium, generating helium-4 and a high-energy proton. Combining protium and boron-11 leads to aneutronic fusion, which releases no neutrons but produces energetic charged alpha particles convertible to electrical power. Aneutronic fusion aims to reduce material activation significantly and can potentially provide more efficient energy harvesting pathways. A highly promising fuel candidate for aneutronic fusion is proton-boron fusion, offering advantages in material science and non-proliferation concerns compared to other fusion reactions. Among the studied materials are pure metals like tungsten and beryllium, as well as compounds such as carbides, dense oxides, and nitrides. The preparation of well-adhered barriers through coating techniques emerges as a crucial focus in research, particularly emphasizing methods involving oxidation or specific gas environments with magnetic and electric fields. Evaluating barrier performance remains a significant challenge, with gas permeation through classical coated membranes persisting as a reliable method to determine hydrogen permeation barrier efficiency. In response to the burgeoning designs for fusion power reactors anticipated for 2040, the United Kingdom Atomic Energy Authority released the UK Fusion Materials Roadmap 2021-2040. This roadmap targets 5 priority areas, concentrating on advancements for tokamak family reactors. These include the development of novel materials to minimize activation in the fusion power plant structure, optimizing compounds for tritium fuel breeding, creating irradiation-resistant magnets and insulators, enhancing structural materials to withstand neutron bombardment at elevated temperatures, and ensuring engineering assurance for fusion materials through irradiated sample data and predictive models to instill confidence in their suitability for forthcoming commercial power stations. In fusion reactions where a plasma is enclosed in a magnetic field, the fusion rate scales with the 4th power of the magnetic field strength. As a result, companies relying on magnetic fields to control plasma are exploring high-temperature superconducting devices. In 2021, SuperOx, a collaboration between Russian and Japanese entities, unveiled a new manufacturing technique for superconducting YBCO wire designed for fusion reactors. This innovative wire demonstrated the capability to conduct between 700 and 2,000 amps per square millimeter, with the company successfully producing an extensive length within a short time frame. Containment considerations in fusion reactors involve withstanding substantial thermal loads, neutron radiation causing activation and embrittlement, high-energy ions, alpha particles, electrons, and various forms of light radiation. Depending on the reactor design, factors such as electrical conductivity, magnetic permeability, and mechanical strength are crucial, while also ensuring that materials do not transition into long-lived radioactive waste. Accident potential and its impact on the environment play a crucial role in the societal acceptance of nuclear fusion, also known as a social license. Unlike fission reactors, fusion reactors are not prone to catastrophic meltdowns. They require precise control of temperature, pressure, and magnetic field parameters to sustain a net energy output. Any disruption to these controlled conditions would swiftly terminate the reaction. Fusion reactors function with only seconds or microseconds of fuel supply at any given moment, and without active refueling, the reactions cease immediately. This operational design effectively prevents runaway reactions that could lead to disasters. Despite having a plasma volume of over 1,000 Ur3, the fuel content within the plasma is minimal, typically just a few grams. In contrast, fission reactors are stocked with fuel that can last for months or years, making them susceptible to meltdowns due to the abundance of fuel. In the context of magnetic containment, the strong magnetic fields generated by coils are mechanically secured within the reactor structure. A failure in this structure could potentially release the tension of the magnets outward. However, any resulting event would be akin to industrial accidents or the quench explosion of an MRI machine and could be effectively contained within a designated building similar to those utilized for fission reactors. On the other hand, in laser-driven inertial containment, the larger size of the reaction chamber reduces stress on materials. Although the possibility of a reaction chamber failure exists, halting fuel delivery can avert catastrophic consequences. A magnet quench is an abnormal cessation of magnet operation that occurs when part of the superconducting coil exits the superconducting state due to various factors such as excessive magnetic field or rapid changes in field strength. When a magnet quench occurs, rapid Joule heating causes the entire magnet to transition to a normal state over several seconds, accompanied by loud noises and cryogenic fluid boiling away. While permanent magnet damage is rare, localized heating, high voltages, or mechanical forces can cause component damage. However, safety measures are typically implemented to detect and mitigate quenches. In situations where a large magnet experiences a quench, the evaporating cryogenic fluid can present an asphyxiation risk to operators. Notably, a section of superconducting magnets in CERN's Large Hadron Collider experienced an unexpected quench during startup in 2008, resulting in the destruction of multiple magnets. Regarding atmospheric tritium release, fusion reactions naturally produce harmless helium, but retaining hazardous tritium completely poses challenges. Despite tritium's volatility and biological activity, the health risks associated with its release are relatively low due to its short half-life and low decay energy. Fusion facilities like ITER are equipped with total containment structures for tritium. Calculations indicate that a typical fusion power station would contain a small amount of tritium and other radioactive gases, with releases diluting to legally acceptable levels by the station's perimeter. The likelihood of minor industrial accidents involving the release of radioactivity or injury to staff in fusion reactors is estimated to be lower compared to fission reactors. In terms of radioactive waste, fusion reactors generate significantly less radioactive material than fission reactors, with the generated material being less biologically harmful and decaying within a manageable timeframe for safe storage. While fusion reactors initially produce radioactive waste comparable to fission reactors, the shorter half-lives of fusion byproducts mean that the radiotoxicity diminishes rapidly. Fusion waste typically retains radioactivity for about 50 years, with some low-level waste remaining radioactive for an additional 100 years. The short half-life of fusion waste eliminates the challenges associated with long-term storage, with its radiotoxicity comparable to coal ash within 500 years. However, classifying fusion waste as intermediate-level waste instead of low-level waste may complicate safety considerations. Fusion reactors offer more flexibility in material selection compared to fission reactors, enabling the use of low-activation materials like vanadium and carbon fiber, which have lower radioactivity levels. Furthermore, in terms of fuel reserves, deuterium and lithium are commonly proposed as fusion fuel sources. Current estimates suggest that known lithium reserves could last 3,000 years if fusion maintained the energy output of 1995. Additionally, using deuterium alone could provide fuel for 150 billion years, far exceeding the Sun's remaining lifespan and the age of the universe. Such extensive fuel reserves highlight the long-term sustainability and potential of fusion energy as a viable power source. Research funding for fusion power has seen substantial investments, with the European Union, the United States Department of Energy, and private investors channeling billions of dollars into projects like ITER and DEMO. While the economic hurdles for tokamak-based fusion power remain significant due to high startup and maintenance costs, advances in computing and materials science have paved the way for the development of fusion pilot plants, FPPs, by the 2030s. Public-private partnerships are emerging as a model for funding these projects, with plans for commercial pilot plants to be operational by the late 2020s, potentially reshaping the energy landscape. However, the economic viability of fusion power is under scrutiny due to the plummeting prices of non-nuclear renewable energy sources. Fusion plants are projected to face challenges in cost-effectiveness, with high initial capital investments and ongoing operational expenses. Despite the competitive cost projections of renewables like solar and wind energy, fusion power could still play a role in complementing renewable sources, especially in filling energy gaps and supporting energy justice objectives. Socioeconomic studies and strategic national initiatives are beginning to explore how fusion power can integrate with existing renewable sources, potentially serving as a reliable baseload energy option with thermal storage capabilities and cogeneration potential. In April 2023, a significant decision was made by the NRC to regulate fusion energy under the same regime as particle accelerators rather than fission, potentially influencing other nuclear regulators. This move was paralleled by the UK enacting the Energy Act 2023 in October 2023, making it the first country to legislate fusion separately from fission, in support of planning and investment for their planned prototype fusion power plant for 2040, known as STEP, and collaborating with Canada and Japan in this endeavor. While attaining substantial contributions by 2100 remains conceivable, the extent of these contributions hinges on technological pathways, particularly related to cost considerations. Recent developments post-2020 have set the stage for what some term a new space race involving multiple stakeholders, notably the US, China, and the UK's STEP FPP.